Okay, let me update you on a few things. Actually, instead of just loose ends, there's one critical thing that we need to go through. So remember, in the beginning we defined these stresses. It depends on elastic stress, or here we define total strain minus plastic strain. So one thing we have to do, we have these zeroed out. So you need to go in and using the definition I gave you, this is my plastic strain. So this gamma times the slip, direction, and plane. Here's for the other normal strain. And our shear strain is made symmetric like this. Alright? Everything else is the same here. I've gone through and I've checked a few angles, and I found parameters that should work reasonably well. The other thing I did is, here's the displacement I'm using on the surface. So this is what you should use for the homework. Currently I have a beta set to 1 to stabilize the problem. Here's my material coefficient resisting dislocation motion. So it's C11 divided by 10. I'm dividing this by 100. Turned out 1,000 lattice instabilities. I've currently checked 40 degrees for the angle, and let's use a critical shear of 1 e to the 8th, and all these units are Newton meter second. Alright, I believe that's all that's changed. The one thing I do is I change the results while solving, so I'm plotting the results. And here's what we have right now. Let me let this solve so you can see how this evolves. So you're going to see initially no dislocation density. So it's going to be fully zero or green. And at some point dislocations will start propagating in. That's because right now the shear stress hasn't reached the critical shear or the yield. Right here it does. And as we continue pulling, that plasticity zone starts growing. So this will continue growing up to some point, and then if we run this simulation out long enough, this should saturate to a fixed dislocation density, and that's what we want to check. So that's the way we're going to analyze this problem to figure what is the critical angle. So if you go to derive values and do integration, surface integration, pick our one and only surface, add it, and let's take gamma squared as a measure of dissipation, and now we evaluate. So this isn't solution 1. So in solution 2 this should work. Okay. So you notice this is pretty constant after about 1.6 seconds or 1.7. So we know we've run this out far enough. If you want to further check that, if you click this button, oh, so that's interesting. Overshoots. In that case, what I want to do, so I want to go back, reduce our time step. Let's rerun this now, see if these results will be any different. That could create an instability. Remember, I'm using a strict time step because COMSOL has its own internal time step where it tries to figure out how to step forward in time. Remember, there's critical time steps where things can go unstable. I'm putting that in as a fixed value, so you can continue reducing that if you do see an instability. So let's see what happens here. Let's see if the result will be any different. Alright, let's go back to my surface integration. Let's evaluate this again. Interesting. That did not change. Let's try something different. Let's make this a little bit bigger. Let's double it. What that should do is dampen out that solution so you don't get an overshoot. Let's see if that works. Now it may not run to full equilibrium, but we can always increase the time of our simulation. So it goes up to 7. Oh, and it just dropped down again, but the overshoot may not have been that big. Alright, let's check it again. That is interesting. So that is not changing. So we may not be in a range where we see any change. So I'm going to investigate this, and then we will push forward to determine what are the key or appropriate parameters to solve.